So I am Mohammad Munib Saad, and I'm doing my PhD in computing under the supervision of Dr. Rory O'Reilly and Dr. Bashir Hussain Rahmani. Today, I'm going to talk about generated residual networks and their potential training challenges. So my work is about addressing the intra-class mode class problem using the adaptive input image normalization in gain-based X-ray images. So generative residual networks have been widely utilized in the area of biomedical image analysis. They have been used for image synthesis, image detection, image segmentation, image reconstruction, and so on. So there are a lot of training challenges in gains such as mode collapse, non-convergence, and training instability. And actually, the deep learning researchers have been facing challenges of data limitation in the area of biomedical imaging analysis. So it is strongly recommended to use generated residual networks to address the data limitation problem using the data augmentation technique. So this technique will help to improve the classification performance of deep learning models, as well as improve the different application performance, such as predictive analytics. So let's dig into the gains. What are generated residual networks and how they work? Basically, gains are class of machine learning techniques that generate synthetic data based on training data. So it is a learning agent that can learn features of real training data and try to generate realistic synthetic images that can look like the actual real images. So it has two main players. The first one is the generator. It takes random n-dimensional input feature vector Z and generate a noisy image G of Z and give it as an input to the discriminator. And the second player is the discriminator that is responsible to classify the synthetic image G of Z from the real image X. The discriminator also provides a feedback to the generator in the form of gradient weights. And based on that feedback, the generator updates its learning and try to create realistic sample that can looks like the real sample. So the gains use game theory, minimax game theory, and here is the loss of discriminator for real samples, and this one is the loss of discriminator for synthetic samples. So the first main problem in the training of gains is the mode class problem. What is mode class problem? Actually, when the generator generates similar kind of samples for a number of different input samples, let's say we see in the upper row, we have different samples of real images. And if we look at the bottom row, we have synthetic samples of same kind for a different real input samples. So this is a mode collapse. When generator collapses all different modes into single one. So it degrades the diversity of generated samples, and it also degrades the performance of gains in respect to the synthetic imagery. So we use multi-scale structure similarity index measure and free shape inception distance to differentiate synthetic images from real one. And we quantify the mode class problem using multi-scale structure similarity index measure, and we quantify the diversity of synthetic images using the FID score. And we can see that we measure this real MSSIM score as well as the synthetic MSSIM and FID. Actually, how can we know about that our synthetic images are actually incorporating mode collapse or not? We see that when the MSSIM score of synthetic images is equal or lower than the real MSSIM score of real images, then we can see that, okay, our synthetic images are relatively better and they are relatively have good diversity score. But if our synthetic images have MSSIM score of greater than the MSSIM score of real images, then we can see that, okay, we are facing some kind of mode collapse in the synthetic images as compared to the real one. And similarly about the FID score, FID score basically gives us the feature distance between the distribution of real sample and the distribution of fake samples. So the lower FID score, we got the better diversity of synthetic images. Let's dig into the more detail in the next slides. So we contribute in the this pipeline of generated residual networks to address this mode class problem. So we use adaptive input image normalization to improve the feature information of our X-ray images, so that the discriminator and generator can better perform in order to generate synthetic images. And we use this pre-processing technique that is based on the adaptive histogram equalization. Actually, this technique divides an image into non-overlapping windows, and the normalized histogram of all those windows and using a contrast threshold. And we use this technique before the DC gain, and we use the empirical analysis of different values of parameters such as contrast threshold as well as window size to see which kind of parameters are performing better in order to generate diversified synthetic images. And this is an architecture of deep convolutional generated residual network that we call as DC gain. So this is our contribution as pre-processing step. And let's see, these are the quantitative analysis, results analysis of our work, that we use 3 different kind of windows: 4x4, 8x8, and 16x16. Basically, we choose different window sizes to visually inspect the image features. And we see that by increasing the window size, our feature information of X-ray image will be degraded. That's why we stopped at the window size 16x16. We visually inspected the higher window sizes as well, 32x32, and so on, like this, but they degraded the image information. And we also use a contrast threshold of like 0, 5, 10, 20, 50, 100. And we compared all these performances with respect to the unnormed images. And we can see that as the window size goes higher, our FID score is going to improve, because the lower the score FID is, it means that the diversity becomes better. But this is also not good, because by hiding the window size degrades the feature information of images as well. And if you look at the MSSIM score, this is also, we can see that the difference of real and synthetic MSSIM score of 2 images. And this analysis, and we will see, we use 3 different parameters: batch size, window size, and contrast threshold. Based on 3 key parameters, we perform our empirical analysis, and we can see that at some stages we got best score using the batch size of 134, and for some window sizes, and we got the best score using batch size 67. If you look at the final, if you look at the window size 16x16 of FID score, we can see that we got a best score using the batch size 134. And similarly, if we look at the window size 16x16 of MSSIM, we got the best score using the batch size 67. So this is a quite difficult analysis to understand which kind of parameters we can utilize to improve the feature improve the feature information and enhance the visual information of X-ray images to utilize for DC gain. So we have also tried other pre-processing techniques such as Gaussian filtering and mean filtering to compare our this adaptive input image normalization. But still we got the best score using these Gaussian and mean filtering techniques. But there is also an issue with these techniques that they blur the edges of objects in the images. So that's why these techniques are not helpful to enhance or improve the feature information of an images. So, but still we want to see that how these pre-processing techniques can incorporate to improve the feature information of images, so that we can generate and highly diversified synthetic images. So here is the results that we conducted for our work. We can see that in the at the very top, we can see that we have MSSIM score comparison and the FID score. So from going from left to right, we can see that for unnormalized X-ray images, we have higher FID score. And as we applied the normalization on the images and perform DC gain for generating synthetic images, we got a lower FID score, and similarly, we got improved FID score using the higher window sizes. But if we look at this stage, the last window size 16x16, we can see that our image information is going rough, and it actually loss of feature information. So, and MSIM score, if you look at the very first one, unnormalized X-ray images, we can see that we have real MSIM score of 0.521 and synthetic MSIM score of 0.575. And this is a difference of almost 40 plus. And if you look at the normalized window size 4x4 using contrast threshold 10, we can see that the difference of real and synthetic, it lowers the difference between real and synthetic, which means that this technique is helpful to generate highly diversified images using as compared to the unnormalized approach. And similarly, we conducted this for window size 8x8, and we can see that this can more lower up the difference between real and synthetic MSIM score. And similarly, for 16x16, we can see that we have a lower difference between synthetic and real MSIM score. So this is the process we conducted our empirical analysis using these three different techniques. So now we can see that, yeah, and we generated synthetic images using this DC technique and the adaptive input image normalization approach. And then we use that synthetic images with the real images, and we perform a classification of healthy X-ray images using these gain-based generated X-ray images. And this is the detailed analysis of classification performance of healthy X-ray images. Actually, we use a limited data set that contains pneumonia and healthy X-ray images. And in that data set, we have a minority class of healthy images, and we augment that minority class using this using our approach DC gain with adaptive input image normalization. And then we perform these different combinations of gain-based generated images using the CNN, convolutional neural network. And we can see that we got different behavior of accuracies using the specificity as well as recall scores. And we got the best scores using this window size 8x8 and window size 4x4. And we got the best specificity. Why we look at the specificity score? Because the CNN is looking for pneumonia images, because that is the majority class. That's why that is considered as a recall. And we are interested to look for healthy class, and that is a minority class. That's why we are interested in the specificity score. And we look at the specificity score, whether our performance can improve the classification or not. And we choose and how we choose these kind of combinations to classification performance. and we selected best MSSIM and FID scores, window sizes, and then we perform this performance. So if we conclude our work, we can say that the adaptive input image normalization is helpful to improve the performance of DC gain-based generated X-ray images, and it has the capability to generate highly diversified synthetic images as evidenced by the FID as well as MSSIM scores. And this technique is also helpful to enhance the visual information of diverse features in the X-ray images. And so, yeah, as there are pros, there are cons as well. And this technique has a lot of limitations as well. The one limitation that we saw in our analysis, this is very sensitive to select these parameters like window size and contrast threshold, because X-ray image has a lot of vital information inside it, like chest structure, like ribs and spine, and these kind of information. So we have that, we use healthy X-ray images. That's why we have to keep each and every information in that image. But if we use a diseased image, let's say COVID-19 X-ray, chest X-ray image, so we have to keep only that region of interest of disease information. So it is very sensitive to select window size and contrast threshold, so that we can only enhance that feature region that we are really interested to work on, that we are interested to look upon it. So this is one of the challenge that we can see in it. And we can also improve the performance of this technique by implementing some other technique. Let's say we use contrast morphological feature. So we can also consider other features to widen our research area. So this is our technical work, and this is also available online at the archive. So this concludes the presentation, and if any question, I'm happy to answer.
Excellent, Mohammed. That was great. Okay, so do we have any questions? Go for Christian.
Hi, Mohammed.
Yes, hello.
What I probably missed at the very beginning is why, not at the beginning of your presentation necessarily, but why is it a task that would be useful for anything to generate X-ray images using GANs? I'm a little bit lost why this would be useful, to be honest. Would you have any insight into that?
Yes, sure. Actually, we have data limitation problem in the biomedical image analysis, and that's why GANs are used to augment these kind of data sets. And so that's why we use GANs to generate synthetic images, so that we can have a lot of images for training the deep learning models. And that's, yeah.
But then what you're doing here is you're perturbing the input data in a sense. And of course, that creates more diversity. Wouldn't you be then just, if you would just do the red block here and don't run this through some architecture, it would get rid of all the machine learning, I suppose, but it would potentially generate a much cleaner and much more explainable data set that would allow you to come up with the same conclusion, wouldn't it? What's the purpose of the complex architecture underneath generating these probably more smoother images or something? That's what I don't really understand, because at the end of the day, the discriminator will just try to make it as similar to the input data set. And that is what every other learning algorithm would also do, I would say, if you perturb the input accordingly.
Yes.
Or am I missing a point here?
Yeah, actually, we are doing this task because GANs incorporate the training challenges like mode collapse, that is our basic target. So when we have a diverse kind of X-ray images, and the GANs find difficulty to generate all those diverse images as per their diversity measures. So that's why we use this technique and enhance the performance of real images, so that GANs can easily cover each and every specific features of each image during the generation process and give us a synthetic diversified images.
But then how do you avoid introducing artifacts into that? Because at the end of the day, I understand that the GANs will converge to something and they have this particular problem and they will not pick up on certain features in your original data set. But then introducing artificial features will of course increase the diversity in your outputs. But does this diversity make any sense, or is that just replicating what you introduced into the data set then? Because then it would not serve the purpose, I would almost feel.
Yes, this is actually, we are doing the baseline, but diversity can help to improve the classification performance of deep learning models. If you have, let's say we have 3 or 4 different classes of different diseases, and you don't have the diversified images of that can show the diversity difference of each class. So then you can end up with the similar kind of images from all those classes. Then your prediction model is not as much robust that it could be. So that's why we have to generate diversified images that can justify each class separately, so that our deep learning classifier can easily recognize each class with their own diverse features, so that it could be helpful in prediction performances.
But wouldn't that also happen if you just add the perturbed images into your original training data for this other learning algorithm? At the end of the day, the generator isn't super necessary in this architecture. So what's the generator adding, I'm wondering?
The generator is actually learning based on the feedback provided by the discriminator. And this is the discriminator that learns from the real data and take the noisy image from the generator and differentiate these images, both these images, and gives a feedback to the generator. And the generator task is to update its performance based on those gradients that can be fed by the discriminator. So that's why we are doing this image analysis or image enhancement task, by which we can improve the learning of the discriminator, and by doing that, our generator can also generate better images in sense to diversity.
Yes, but what's the purpose? I'm still missing the purpose here. I mean, you're injecting a noise there into the generator. I understand how GANs work, but if you use that for discrimination purposes at the end of your pipeline, if that's the goal, if your goal is to create training data for subsequent machine learning algorithms, then I suppose what will happen is that you just plug a discriminator, another discriminator at the end. And if you, of course, make your data more diverse, this second discriminator will benefit from that. And in order to make this more robust, introducing the noise that you're introducing in your pre-processing as you presented will potentially help. I'm just wondering why it is beneficial to also have this GAN in this architecture that at the end of the day will just, I would argue, create pictures that look a little bit nicer in the process. Whereas for the final classification, you need to look at the random sources that you're introducing. And there's the noise term that you introduce into the generator, of course, and there is the noise that you're introducing in your pre-processing step. And both will, of course, improve the performance, I suppose, of the discriminator. But I'm just wondering if a properly designed discrimination network that you would then use based on the enhanced training data or perturbed training data, if that benefits from having a GAN in the pipeline. Is that something that you looked at or that you're going to look at?
Actually, I have not gone through that, because our sole target is to address the mode class problem in the GAN. So that's why we use this kind of technique only to see that our gains can generate diversified images as or not. You are right, because if we skip the gain model and just use this kind of adaptive normalization technique only with the real data and just include the predictive model and classify the images, that can improve the classification performance as well. But as I already said, this is a baseline empirical analysis so that we can see how these kind of reprocessing techniques can help the generator acellular networks to improve their performances in order to generate diversified synthetic images. But this can be also helpful to use these or induce these kind of techniques in only the classification models to improve their performances.
Yeah, I don't want to take anybody's time, but I'm a little bit lost now, because again, if you just randomly and nonlinearly is the key here, perturb the images, of course you will increase the diversity of everything at the end of the day. It will just look rubbish. And if it's medical images, it's much more difficult to spot, I suppose, for non-expert. But I'm still struggling to see the purpose here. That's really my main question. Why does it make sense to do this?
Actually,
that's what I don't understand.
Yeah.
Okay, we're almost over time. So Christian, why do it? Okay, so like,
yeah, I'm generally interested in the motivation behind things. So I'm generally interested.
He's looking to generate synthetic data. Yes. Okay. For a problem which you've very limited quantity data available. Now, GANs will do that, but they'll suffer from the inter-class and mode-class problem. So it'll repeat the same. It'll spit out the same thing to you repeatedly. Okay, which is kind of nonsense for aiding any addition of data. So the purpose here is that, okay, two things. How do we quantitatively evaluate the quality of data being generated by the GAN? That's an important consideration. And he's using his MSSIM to say what's the similarity between the data that's being generated by the generator. And he's using the FID score to say how far is that in terms of distance from the real data. So we're getting a similar distribution of features that somewhat maps to the distance you'd expect from the original real data, thereby hopefully giving us data that's resembling the actual data we want to generate. Now, at the same time, we're investigating the adaptive input image normalization to reduce the actual occurrence of mode collapse by identifying the prominent features in the images he wants. So like, it's a start to where we go next, okay? But does that answer the question? Are we still confused?
Yeah, I'm just wondering how would you then evaluate this? Because then I suppose you need to do some sort of cross-validation with an unrelated data set and see if the data you generate has anything to do with typical X-ray images in this sense. So and I'm missing something here, but
yeah. Okay, of course you would. You have to find an entirely new data set. So like what we tried to do then was take your pre-existing classifier as a means of evaluating that. So like it was someone else published a paper classifying pneumonia from X-ray, happy days. So re-implemented that, did traditional data augmentation with it to see what's the actual performance of the classifier against the traditional data augmentation techniques versus us adding in our synthetic data that we're generating. And it's just the bare bones, does it bring us closer to an acceptable range of data or not, But again, yeah, there's loads of work to be done on this. That's why he's got a couple more years of work ahead of him to get all that sorted.
Yeah, sorry, I didn't want to hijack the discussion here.
Okay, it's gone 3 o'clock. So are there any questions there quickly, or will I say?
I have a tiny question. I think it can be answered quickly. Yeah. In data augmentation, we upsample data by using randomness. There's a degree of randomness in the change. Mohammed, is there a degree of randomness in this pre-processing step, or will you always have the same transformation with the same image?
Yeah, there is but that is based on these kind of sensitive parameters like contrast threshold and this kind of window size. If you just go by varying these kind of parameters, then you can get different images. But if you fix those parameters, then there is no randomness, and you will generate a similar kind of images again and again.
So in the way you use it, do you just do like a one-to-one mapping, or you think randomness is necessary?
No, I didn't consider that. I just work on these, utilize these parameters and give that data to gains. And in the gain, in the DC gain, we have that kind of approach.
So the upsampling is only coming from the actual generator of the data. Okay, cool, thank you.
And that might be the answer to my question, that this is introducing the randomness into everything. So thanks for that.